And once again, the second speaker of this session, Knut Conradsen from the Technical University of Denmark, Copenhagen. He is an expert in statistical image analysis. Important applications of this kind of analysis are, for example, methods in remote sensing images in order to facilitate mineral exploration, or, for example, mathematical treatment of medical images, or, for example, fingerprint identification. I leave the floor to you.
Thank you. Well, I trust that the 2 minutes missing are taken from the break and not from my part. Well, thank you. It is a great honor for me to be invited to give a talk here, and I will present some results that I have made together with a colleague of mine, Bjarne Kjær Nielsen, and some other of my colleagues have contributed substantially by making some computer programs, and that is very important in this field of work. The outline of my talk will be a short overview of the notion of contextual classification. It will be some results about Newtonian random fields. It will be something about two algorithms I call the Giemann and the Elliott algorithm. And then I'll be talking about estimation of texture parameters for use in classifications, and then I'll offer a conclusion at last. And it's those marked with red that should impress you the most. The others is just reference to other people's work. The other day when I was talking to Finn, I was asking how big Finland was, and he was saying to me, I was expecting an answer around 350,000 square kilometers, but he said to me, well, it's 10 times the size of Denmark. So I have chosen to use this locality map in a Mercator projection. Our images will be taken from the northern part of Denmark, up there, the green part. When there are North Americans in the audience, I often show this conical projection, telling them that Greenland is just an island northeast of Canada. But the images we are taking from that part of the world are basically Lancet images. And the Lancet satellites are orbiting the Earth in an altitude of approximately 800 to 900 kilometers. And for each pixel, that is a square or rectangle on the surface of the ground of the size of 80 by 60 meters for the first 3 satellites, or 30 by 30 meters, you are measuring the electromagnetic reflection in 4 or 7 wavelengths. And thus you have a 4-dimensional vector for each rectangle on the surface of the Earth, and you measure that continuously. Every 18th day, each sector of this size has been measured again. So you'll get an enormous amount of data, and therefore a lot of the models that you'll have to apply have to be very ad hoc. I mean, you cannot think forever on how to use all this information. You have to do some fast decisions and do some computing in order to help the geologists that you are working with to obtain their results. Now, the reason that you can use this type of information in, for instance, mineral exploration can be seen on this image of reflection spectra of different kinds of material. I've shown the wavelength down here of light, and there's an approximation here of the spectrum going from the blue to the red to the infrared. And these 4, 5, 6, and 7 are the channels number 4, 5, 6, and 7 on the Lancet scanner. So these are the places where we are measuring. And you can see that vegetation is green. It has a peak here in the green area. And you can see here that some types of rock has a rather smooth curve, and other types of altered rock has a dip here in the infrared area. And those rocks here are interesting for geologists. These alteration zones often show presence of mineralizations, and therefore the information present in the Lancet satellites are useful to geologists. Now, in the good old days when people were classifying Lancet imagery, they were just using ordinary discriminant analysis. And that went fine. There were some problems with biasness of the estimated dispersion matrices because of the obvious correlation between neighbor pixels. But basically it went on okay. But then when the new high-resolution satellites emerged, people found suddenly that they had problems. They got worse classification results because of the better resolution. A forest is no longer a forest. A forest is some pine trees here and maybe a green spot here and maybe a big rock here. And therefore they got misclassifications. From a purely physical point of view, maybe it wasn't misclassifications, but they wanted to look at it as misclassifications because they just wanted to have this as a forest type of answer. And therefore, people started wondering about how to introduce spatial continuity in their models. And a lot of suggestions were made. You could say that this could be some of them. You could have some neighborhood classifiers that introduce Markovian models for the populations themselves. You may do segmentation by means of Gibbs models, where you again have this is also some kind of Markovian structure. Or you may use some kind of texture measures that are smoothed over some areas in order to obtain these results. And there's been a very extensive literature in recent years on these neighborhood classifiers. And you could say that a general concept of a neighborhood classifier could be something like this. You are considering, for instance, the 4 nearest neighbors for this center pixel, and then you augment the observations. You originally have the DT, and then you augment it with the values of the neighbors, and then you have a class identifier and the augmented part there. And then you can make a base classification scheme, and you'll have different types of classifications for different types of models of the continuity of the populations. And I'll show some, or one at a later stage. Now, for those people who are smoothing the data instead of using these parametric descriptions, this result, which I have taken from a paper of Switzer, is very nice, and that says that it is okay to smooth under not too restrictive assumptions, then the smoother. Then using the ordinary maximum likelihood classifier is the optimal solution to the classification problems. So if one originally were smoothing the data, then it may still be considered okay. Another way of cosmetic treatment of such data is to make a smoothing afterwards, and this is just a cosmetic type of thing. If you are having salt and pepper noise on your classified image, then you may remove some of it by some kind of median filtering or other types of algorithms, and that may improve the visual quality of the image, but of course not the actual content of it. Now, some of the models that have been very popular lately for images are Markovian random fields, where you basically have a condition like that the probability of an outcome in a pixel given the rest of the image just depends on pixels in the neighborhood. And then the question is, of course, which kind of neighborhood structure should you impose? And I'll show you some examples that are just made on binary images. I think that may make it easier to understand what is going on. At first order, Markovian random field has simply this neighborhood structure. You're having the north south and east west neighbors, and with those neighbors, you get easily the conditional probabilities. Will follow that law there, and that is very easy to compute in, and you may very easily simulate images following this type of model. Now, this model is also known from statistical mechanics. You can show that the joint probability distribution follows this expression up here, and these sums here are, well, it's described as efficient statistics, and they are given by the cliques in that neighborhood system. I have a very nice remark from a paper by Hafner and Splansky about the equivalence of this and statistical mechanics, and it says that the practical significance of the equivalence between these models and the things known from statistical mechanics is limited because of the obscure language of statistical mechanics. And I think that anyone who have tried to get some results from statistical mechanics will acknowledge that this is really a correct description of the way they are stating their theorems. But however, these models are known as Ising models since 1920, the 1920s, I guess it was in 1926. So the theory has been known for a long time, but due to the computational complexities, very little work has been done in statistical image analysis using these results until quite recently. This was a simple first order structure. You may of course expand the density dependence and have a second order structure where you are considering all these as neighbors, and you may write down again the conditional probabilities, and there's no need for looking at those formulas. Now with such parameters you may simulate images, and this is a simulated version of a first order field, and there are 40% black pixels in this image. Now if you look at the next one, it'll again contain 40% black images, but you can see it has a different texture, it looks different. And if you're taking a second order one, it may look like this, and again it contains 40% black pixels. So these images are obviously not different because of the mean values, the amount of black pixels, that's 40% for all of them. So if you want to discriminate between images like this, you'll have to look at the correlation structure, or as one often says, at the text. Now one can make, of course, some very naive discrimination between such patterns by if you really know the distinct models, by simply choosing model I, if and only if the probability for the I's model is bigger than the probability for the J's model. And that works also out relatively nicely. I have here an example of two images that up here that are similar or generated by similar processes. The one is just turned 90 degrees with respect to the other one. And down here I have classified each single pixel up here by means of those two known models. And you can see that you definitely have more black pixels over here than over here. So this point-wise classification, of course, gives some useful results. But more sophisticated work has been done lately in these types of things. The first type of model is, I call the Elliott model, and that is some kind of signal plus noise model, where as well the signal as the noise are following some kind of Markovian structure. And using a lot of simplifications on the spatial dependence, it is possible to maximize the likelihood function of this model. The log likelihood function will look like this. And if you're introducing these simplifications, which just restricts the dependence to being north-south or east-west, and not both, then it is possible by means of dynamic programming simply to maximize the likelihood function. And I'll later show an example how that is done. Another approach, also using these Markovian random fields, or the Gibbs random fields, is introduced by the brothers Gieman and Gieman. And their main contribution is not as much using this random field. I think personally that it is they also introduce a line process in order to distinguish between different areas of the image. And by doing so, they may obtain sharper edges in a segmentation of images. Maximizing the likelihood function in this case is again a question of maximizing a function of say 250,000 variables, and that may not very easily be done by gradient methods. It may be done by gradient methods, but it takes a long time. An alternative approach is based on an algorithm known by physicists as the Metropolis algorithm, or simulated annealing. and that works out relatively nicely. I have a very naive example here of an image and a version that has been blurred and corrupted, not very corrupted, just slightly corrupted by noise. And this is what a restoration looks like after 10 iterations. And you may see that it is almost similar, well, it is relatively similar to the original one. And you can see that there are black lines there. We have been using the line process in order to obtain sharp lines. And that is one of the reasons that we're having these nice patterns left in the image. Now, a totally different approach is based on filtering and estimating new feature vectors. And due to the computational problems, Fourier-based filters have not been very popular either within this field. The theory of Fourier transforms of functions of two variables is extremely similar to what is known for functions of one variable, and you may define the same types of filters, convolution filters, and by a suitable design of the weights, you may obtain filters that are good at estimating lines and edges in an image, or that are good at estimating the local frequency in an image. And I have here, I can show here a couple of such Fourier filters. The other ones are, these two filters are called quadrature filters. They are, or it represents a partitioning of the original function in an odd and even part. So you're having a cosine component and a sine component, and the sine component corresponds to an edge detection, and the cosine component corresponds to a line detection. And then you may rotate these filters and estimate lines and edges in different parts of the image. And then you can combine those results to a single estimate of the local orientation in the image. By using different widths of these parts here, you may similarly obtain estimates of the local frequency in an image. And by using such filters, we may obtain very good results on classifying imagery. This is a Lancet image from the southern part of Greenland, and the results I'm going to show you are taken, or is a question of classifying an area up here and an area down here. This area is not covered with vegetation, the gray part, and this area here is not covered with vegetation, the gray part. But all of this is granite, and all of this are intrusives. And the red parts here are vegetation. We will take a training set that is just here in the vegetated, in the area with vegetation. And in the first case, you'll see that we are getting some misclassifications, so that the training set down here makes the algorithm, the ordinary classification algorithm, think that, well, this up here comes from this part. And then I'll show you some slides where we are estimating local frequency and orientation, and see how the results are improved. Can you turn on the slide? At the back. This is a black and white image of the scene you just saw early on. And in the beginning, I'll show you some images that are taken from around this area, just to show you what things look like. People in the first row may look at this river here. I'll show a picture of this river. One can vaguely see some ice down here. I'll show you some pictures there. I'll show you some pictures taken from up here, down this way, and some pictures taken from this part here. And just so you can see how it is. This is the river you saw before. The former image was taken from 900 kilometers height, and this is taken from the ground surface. And you can see that the shape was easily recognized on the previous image. This is what the area looks like. Ridges like this one are determining the local orientation in the image, and the distance between such ridges are determining the local frequency in the image. For Scandinavians, this place is of some interest. This is a place where Erik the Red and his son Leif Erikson had their first camp, and this is from the place where Leif Erikson supposedly went to North America 1,000 years ago. This image is taken from the top of the fjord, and the mountain you are looking at here is the intrusive I was pointing out earlier on. And some of the things that are changing the amount of frequency is that you can see this is a very smooth surface, whereas up here we have vegetation and we have small lakes patched all over the area, and that gives some of the dispositions. You may see the ice barrier here, and you can again see that we are having vegetation on top of the soil, but we have a lot of lakes here that are determining the texture, and that is why it is possible for us to discriminate between such rocks and such rocks, although we have the vegetation to cover the result. This is the ice ridge seen from above, and this is again the ice ridge and a three-colored version of the image. This is, of course, not natural colors. The infrared channel has been painted red, and that is why you are seeing all the vegetation as red in this image. Well, just in this part here, there's an old airstrip, and I just show you this image so you can see how the image is built up by pixels, and all these pixels here are 50 by 50 meters, and you can see the rest of the airstrip. That is the remainders of an American base built during the Second World War. Now, for the classification, these are the training sets I have taken. These are the granites and these are the intrusives. And in order to make a complete classification, I have taken some other representative samples of water and some sandstones and other geologic units. That's not very important. The important thing is to discriminate between these two parts. And this is what you obtain by an ordinary maximum likelihood classifier. You can see here that we have the intrusives are also depicted up here, and that is of course because the spectral signature is similar. They look the same, they have the same type of distribution. But if you are looking at a high frequency emphasized image, you can see that the general type of orientation is the same, irrespective of whether you have vegetation or not. And therefore, if you estimate the local frequency by these kernels I showed you earlier on, then it should be possible to make a better classification. Well, this is a close-up of the coefficient, or here the coefficients in one of the kernels is shown as an image, and this is a collection of the kernels used in the orientation estimation, and these are the kernels used in the frequency estimations. They are sizes 11 by 11 and 15 by 15, and it is very time consuming to make convolution filterings with these types of kernels. One estimation, like for, well, I'm going back. One estimation of such an orientation by means of such a kernel set would take you approximately 5 hours CPU time on a VAX 750. So it is very important that you have adequate computing equipment in order to do these types of analysis. Oh, sorry. Now this is a test image just to show you what the estimate of the orientation will be. It's depicted as colors. You can see out here we have vertical parts, and here we have parts going northwest, southeast, and you can see that they are having colors like blue, and blue of course because they're parallel, and green for vertical parts. And you can see that the orientation is independent of the frequency in the image. This is the image again, and now I'll show you how the frequency varies, and you can see that we're having higher frequencies in here, and then it goes out, and as red you have the low frequency parts of the image. This is then an estimate of the local frequency in the image, and you may see that there are definitely differences from this part to this part of the image, and this one is an assessment of the local, no, the other one was local orientation, and this is local frequency. And you can see that the intrusives here are having very low frequency parts, and whereas you're having higher frequency components up here. And if you're introducing those in the same classifier as early on, you will see that the misclassified parts over here that were depicted as intrusive have disappeared. They were looking like this. You can see they were violet early on, but this part has now become green, and you only have a little tiny spot up there. Fortunately, if you are looking at a geologic map, you will see that there's a very small intrusive up here, so that is of course satisfactory. You may of course use these things in other types of classification, but before I show you that, I'll show you one of the images I promised to show you early on. This is a satellite image of a mountain called Malmberg in East Greenland, and the question is to classify these glaciers and the rock here. And from an aerial photo of the mountain looks like this. This reddish part here corresponds to an alteration zone that is connected with a molybdenum mineralization. And what is very interesting is to be able to depict areas like that in the classifications. And since it tends to disappear in an ordinary discriminant analysis, we thought that introducing a contextual method with a spatial continuity might improve it. But you'll see that the spatial continuity extended the glacier over the area and did not improve the results. So, I mean, it's not enough to introduce these types of spatial continuity. You have to be very careful with your feature vectors when you try to classify. This is a piece of, it's a wood slab, and we have done some work here in order to make a routine for quality control of wood slabs. And a major problem is the presence of knots. Now, dead knots or knots representing dead wood are easy to classify because they look very black in an image, but this is a live knot, and you can see that it has the same color as the rest of the image, so it's not possible to classify this just by means of an ordinary discriminant analysis. But if you're estimating, again, the local orientation in the knot and smoothing this, you can see that you're having definitely differences between the knot part and the rest of the wood. This is an overlay of the orientation on the original image, and you can see that the knot is characterized by parts where the orientation differs from the green part that would normally should be looking like. So again, these feature vectors are very good in depicting those things that you can see with your own eyes, and which makes it possible to make a visual classification and therefore also to make an automatic classification. I have, will you take it down for me? We have been working very extensively with these types of feature vector generation, and I would like to show you a few more images from the area before I end. This is the first area again, and I can show you some time series taken along those lines. And if you look at those, you'll again, this is from the upper part, and this part here is from barren rock, and here you have from vegetation. And you can see you have a shift in level, but not so much in the frequency aspects of the time series, whereas the other time series definitely looked very different from it. It has the same level as the first one, but it differs very much with respect to the frequency parts. And if you try to fit, for instance, armor models to this, you'll realize that the models become very different in the two cases. So I don't think that it is immediately possible to build a model that includes all these facts in one statistical classification routine. I think that you really have to estimate the relevant features in some way. And therefore, my conclusion will be that it is not very likely that the refinements in these neighborhood-based classifiers will do the job. I think that it is very important also to do these types of pre-processing on the images in order to obtain
useful results. Thank you.
Thank you.